Hey, minasan, konnichiwa, Samurai Engineer desu. So let's resume in this video our discussion, the rest of the discussion on Module 5 of Bridge Engineering Plan. So we are going to show you the Module 5, which was again and again repeatedly explained, and last meeting up to a certain point. So we stop on a particular slide. So let's go back to that one. So bridge engineering plan, set of engineering plan. What are the requirements? Okay. What are the organization and context of the whole set of bridge engineering plan? So we have the plan and elevation. We are through with this. And typical section. So please take note of this. This is the number 2 typical section. Okay, and then we are through with that. So let us explain this one. So this is actually typical section, but it is a what? Enlarged view of the typical section. So let's try to find out if we can explain further anything about this slide. So let us make this slide bigger. Okay, so it's now a little bit bigger, and you'll notice we can read the text right now. Can anyone confirm? Can you read the text? Can you read the writings on the drawing? Please confirm. At the same time, confirm the sound. Sound check if our sound is clear enough for you to understand. Okay, readable and buzzable, and what are the confirmations? So thank you for confirming. Buzzable, readable, and hearable. Can you hear it? Can you hear the sound? So hearable. So clear sound. Okay, thank you. So let's continue therefore. So what can we take out from this drawing? So as a whole, so we are able to explain this one by one. Last meeting now as a whole. So this is the edge of the pavement or the bridge. So this is the edge section. So this is the actual flooring, okay, where the cars, vehicles are about to use. So the top portion or the top layer of this is what we call wearing surface. So wearing surface, so there are about what? How many? 4 to 5 layers. Okay, so 4 to 5 layers, and the top layer is what we call wearing surface. Okay. So this is our concrete barrier. Typical. Okay. Now, it is clearer to us that this one is 34 of number 4 B bars. Okay? So, from this point, going to the next, okay? From this point, going to the next, okay? So, going to the next important reference point, there are 34 of number 4 B bars. So, we can show you the bar sizes at the same time. Okay, so I will show you the bar sizes. Okay, so in your screen we have the bar sizes here. Okay, so these are the bar sizes. I will make it like this so that you can see the bar sizes. So I think it is clearer by now. Okay. So the bar sizes using English units, so are this column. The bar sizes using SI units are on this column. Okay. So therefore, let us increase size. Okay, so it is readable by now. So number 4. So the bridge engineering plan is English unit. So let us look on this column. So number 4. What is number 4? This one. Number 4. Meaning that is 0.5 inch diameter. So in is a unit that is 13. Okay, 13 M or 12.7, the exact value of diameter. Okay, so number 4. That is what we mean by number 4. Okay, take note. Take note. Yesterday we showed you the bar number 9. Okay, I showed you the bar number 9, and what is the area of bar number 9? Okay, 1 square inch. When we are doing the design for reinforced concrete, okay, we use the bar number 9. But in this bridge, we are using bar number 4. But there are 34 of them. There are 34 of them. So the area square inch is 0.2 and the diameter is again 0.5 inch. Okay. These are the list of bar sizes. Okay. Now let's go back to our plan. Okay, so that is what we mean by this part. Okay, B bars, meaning we have similarities. Similarities about this type of bars. That's why we call it B bars, and we call the other one A bars. So B bars are the type of bars. Okay. Okay, so we can compare it to the A bars. So let us find out where are the A bars. Can you see the A bars? These are the B bars. Where are the A bars? Let's go back here. 62. Where are the A bars? A bars, where are you? So, okay. So, A bars are there. Okay, so here. So, these are the A bars. Okay, A bars. Okay. So, therefore, B bars are laid on the bridge parallel to the direction of the bridge. Right? Okay, so that is what we are able to confirm. So by comparing it to the A bars. So there must be what? The definition or legend so that we can there must be a legend in this engineering plan so that we can compare or we can have the definite description of what is B bar and A bar. So B bar is parallel to the direction of the bridge while the A bars are perpendicular to the direction of the bridge. So that is what we are able to find out. Okay, what else? K bars. So there's another definition for that. Okay, so look at the K bars. It is letter S and with splice. Okay, so this portion is the splicing. This splice portion here. Take note, there is the plan, there is a specific location for splicing. Okay, those of you who are into construction, I always noticed in actual, you are not following the correct location of splicing. It is being designed. The location of the splice is being designed. That is not wild guess. So you are not following. Most of the engineers in the construction, in actual construction, is not following. They are not following the design splicing location. Okay, so I'm telling you, they are located that way because they are designed that way. Okay. So what else? High beam bolster, low beam. Okay. So as you can notice here, K bars are sized at number 5 by number 5 bars. What do you mean by number 5 bars? This is the size of number 5 bars. Okay, and number 5 here is the size 0.625 inches and 0.31 square inch area. Okay, that is number 5 bars for K bars. Okay. So meaning there are two of them, two number 5 K bars typical over interior girders. Okay, interior girders. So we have exterior girder and interior girder. So this is what we call exterior girder. Girder 1 is exterior girder. Girder 2 and so on are interior girders. The same is true when we are studying theory of structure framing. So the framing in column location, we call it exterior column, interior columns. Okay? The same is true. So here we are calling those beams as exterior girders, interior girders. Okay? So these are the things that you are going to inspect when you become a civil engineer. Going to the site. It is not your responsibility to just talk and exchange pleasantries and greetings with foreman and workers at the site. You have to inspect their work according to the engineering plan. Like this. Okay, so you have to understand each and every details. Okay, so now there's a question. Sir, do we have an example how to design the splicing of rebars? I usually do it. We usually give that explanation to the student. We have the splicing design. We have development length design. So there are plenty of design that would complete the whole process. However, in this new curriculum, in this new standards and policies for civil engineering, it is not included. Okay, it is not included. So that's why I am only warning you, making you aware of it. Okay? Because if there is no actual splicing design inside the classroom, what will happen when you become an engineer? Okay. You will be misled by the fact that maybe you will conclude that, oh, there is no design of that. You can have splicing anywhere. That's why I also show you failure in construction. Okay? There is a failure in one video. We react to that video. And I show you that the splicing is actually on the same manner. That is a bad design or bad construction practice. Either way, because I do not have the document to decide whether it is a bad construction practice or bad design. Okay? It is supposed to be included in the design, how you could splice it. But I do not have the document, but I have the video. And the structure failed. It fell down. So, I showed you the remaining reinforcing bars. The splicings remain beautifully aligned. Beautifully aligned, but that is not correct. Okay? That is not a correct alignment of splicing. Okay? Probably one of the reasons why it actually fails. Okay? So another question. Is the area rounded, sir? I use the table on problem solving. There is a discrepancy on the answer given in my computation. I use 0.7. I think some uses 0.785. Okay. So that is just rounding up. Okay. So up to the number 8. I already mentioned this to everyone. I already discussed this. Okay. From bar number 2, which is not used currently, we are only using bar number 3 up to number 8. The reinforcing bar is round or circular cross-section. Okay? But number 9 and above, those bigger bars, we are using square. Okay? We are using square in the computation. But in actual, those bars are circular. Right? That is another one standard of practice code that only civil engineer would know. If you are a civil engineer, for example, if you are a mechanical engineer, you will correctly use the area of circle, but according to the code, we have to use square area. Okay? So that is for number 9. But your question is number 8. That's why the problem is only for rounding up. So rounding up error. Okay? Okay. So that is That is the answer to your questions. So you can just put your question there, and from time to time I will answer your questions. Okay. So what else can we see on this plan? Okay. Bay. Typically it's bay. Bay meaning the girder to girder distance. Okay. So that is typical for it. So for example, girder number 2 to girder number 3. That is another bay. So that is bay. And usually these bays are the size of one car or one vehicle. Okay. That is the usual thing to do. So typical here, typical there. Top of slab. Okay. So there are series of reinforcement there. The black dots, those black dots are the reinforcement. So top reinforcement. So or we can say top bars. So this engineer called them as B-bars. Okay. Okay, I will later on explain to you why they are not calling it top bars or bottom bars in this manner. So there is a specific reason. Later on I will tell you about that. Okay, it seems there is no other question. So true, sir, the given table in appendix B, the area is rounded. Okay. Okay, so use the rounded. So the error is only for what? So let us go back to the size. Okay, I will show you. You use size number 8. So you have to use 0.79. But take a look. Okay, if we use three significant figures, that is still 0.79. Okay, this is still 0.79. Okay, this is not three significant figure. This is only two significant figure. So if you use three significant figure, that is 0.785. Okay, so okay. Okay, so however, it is acceptable. It is acceptable even if we are talking about steel design. We are talking about reinforced concrete design. It is acceptable that discrepancy is acceptable because how many times I repeatedly explain with evidence, okay? With evidence and with correct and logical civil engineering perspective, okay? Using the knowledge by the expert. But I mean are the expert from ACI, expert from the author of the book. So I'm using them. Okay, they are the experts, so I'm following them, and I agree that their explanation is the most logical. Okay, so we don't need so much precision, but since we already discussed and agreed to have what three significant figures, okay, you could even have 4 and 5 significant figures in the intermediate computation, so that your final answer would be closer to the uh, to my final answer. Okay? So let us keep it that way. So don't just follow the answer of the book, okay? Because they are the author, they have the perfect reason for that. But it is just between you and me. We agreed that we will use 3 significant figures, okay? Okay. Okay, let's now therefore go to the next slide. Okay. Too small, so let us enlarge this. So let us enlarge by doing this. Okay. It's not yet clear, so let us enlarge it like this. It is the same. It is the same, but it is enlarged using only the typical. So typical meaning this part will just repeat. This part will just repeat on this next neighboring drawing. Repeat and repeat. So this portion will just repeat itself. So let us take a look at this part. So this part is what we call framing plan. So this is the third content of the engineering plan. First page, we have plan and elevation. Second, typical section. Then third is framing plan. This framing plan. So I think it is now much better, much clearer by now. So we have what? Span A is equal to 118 feet. Okay, so span A. There are so many possible spans. So there are what? Span A, span B, span C. So there are 3 spans. So they are just the same. They are just the same. So let us just talk about span A. So span A, 115 feet 9 inches. Okay, center to center bearing. Okay, center to center bearing. So, meaning to say, there is a bearing here. So as you can see, this is the center of the bearing. This is center line of the bearing. The bearing is located here at this line. I mean the center of the bearing is located at this line. Okay? So that is what we mean by center to center. So center to center bearing meaning 115 feet 9 inches to the next center of the bearing. Okay? What else? Intermediate diaphragm. Okay. So intermediate diaphragm, this one. Okay. So 3 spacing at 23 feet 9 inches. So you can, again, you can have your calculator. So let's have our calculator and compute. Okay, 3 times 23 and 9 inches. Okay, so let us have our calculator. I will show you by showing you my calculator here. So let's put on our Casio calculator. Okay, so we have the calculator here. Okay, so we have the calculator. 3 times, what is the span? 23 and 9 inches. Okay, so 9 inches is actually how much? 0.75. 9 inches is 0.75 feet. So 23.75. That is equivalent to 23.75 times 3. So there are 3 of them. So what is the answer? 71. So 71.25. What is 0.25? 0.25 is 3 inches. Okay, but because 3 inches divided by 12 inches is equal to 0.25. That's why, correct, as you can see from the figure. You can see from the figure here, 71 inches, 71 feet, 3 inches. Okay, that is our correct answer. Okay, so what else that you need to know about this? This one, intermediate diaphragm D2, typical of all span. Okay, this one. Okay, it is pointed there, so that is diaphragm. Okay, so in this case, this part is what? That part is actually framing plan. So we are actually having the diaphragm, okay, on our frame. So that is the actual location of the diaphragm on the frame. So in this space, 1, 2, 3, 4. There are 4 of them. Take note of these bold lines. These bold lines. These are the reference lines. We have the reference point here. Take note again. I would repeat, maybe for the last time. Buildings and bridges are slightly different because in construction of bridge, we have the geodetic engineer responsible for giving us the reference point and reference lines. Okay, while in construction of building, actually, because we are economizing on the cost, we don't even need to involve the geodetic engineer. The involvement of geodetic engineer is by giving us the what? The shape and dimension of the land area or the lot area, showing the actual drawing from the description, from the technical description of the lot. Okay, that is the only. However, here there is more about about it because the precision of the location is being highlighted here. No? In building, the civil engineer will just estimate the location of important points, and the civil engineer will decide on which one is the important point. Okay, and that is not correct. Okay, when we are talking about precision and accuracy of measurement. Mind you, before about 30 years ago, civil engineers are allowed to do junior geodetic activities. Okay? Right now, that function of civil engineer was stopped. It was stopped already. So we cannot sign, we cannot certify the location of a particular reference point on Earth. Okay? That is the job of geodetic engineer. Okay? We can just estimate. Any other important thing here? So this E here has a specific definition. It is a legend. Okay? What do you mean by this? CL, so center line. Again, this line is a center line for GDR. Okay? What do you mean by this? Fill, face, and bend. Okay? So fill, face, and bend here. Okay. What do you mean by here? So these are legends. So we can look at the legends and find out what they mean about these symbols, okay, or representation. I am not familiar because they are using their code. We are using our local code. So I'm not so familiar with this. Okay. And diaphragm D1. So we have D1 and D2. D1, D2. So these are the diaphragms for the D1. Typical. So 1, 2, 3, 4. So 4 of them. So these are the diaphragms. Okay. Bent diaphragm D3. So we have. Let us take a look. Where is the bent diagram D3? So to the next bay. So okay, so it is not shown. It is not shown here in our bent diagram D3 is not shown here. Okay. So bent diagram D3 corresponds to diaphragm D1. So on the next repetition of the plan. Okay. So for span B, that is on span B. Okay. What else? Okay. So too small. I can see it clearly, sir. Now, how about now? Can you see it now? So, okay, so I think everybody can see it now. The center line of field splice. Okay. Center line of field splice. This is the center line. So, this is the location of splice. So what do we mean by GDR? Okay. I want to hear from somebody who is listening. If there are any question, I will be the one who asks question. What do you mean by GDR? GDR1, GDR2, GDR3. Okay. So that is from this point going that way, from this point going that way, from this point going that way. So meaning to say, we are using diaphragm, okay, perpendicular to the girder. So the diaphragms are perpendicular to the girder. Okay, so as can also be shown here, so we have 90 degrees, so that is perpendicular. So the general direction of the girder is parallel to this reference line, this horizontal line here. That is the general direction of the girder, and therefore that is the general direction of the bridge. So perpendicular to it is the direction of the diaphragm here and there. Okay. Okay. Any question? So if you can see here on the side, you can see 4 spacing at, there are 4 of them, spacing at 10 feet 9 inches is equal to 43. So we can verify that. If that is correct, we can verify that. Okay, so let's verify it. So spacing 10.75. Spacing is 10.75. So let us replace this by 10, and then press equal sign. We have what? 32.25. 4 times 4. So sorry. So we have to multiply by 4. Yeah. So that is exactly equal to 43, and that is correct. As you can notice on the engineering plan. So 43 feet 0 inches. Okay, so that is the total width of this bridge. Okay. Any other important things here? So we already explained that. So number 4, girder elevation. Okay. At what height? At what height we must put the girder? Okay. What is the height for the girder? For the installation of girder. So let us I think we skip this. We have to go back to this framing plan. Yes, framing plan. We have to go back to this framing plan. We have yet to explain these notes. We have to read these notes one by one. They are very important. Now let's take a look at these structural notes. Let us make them bigger. So let us unshare our calculator. So make our structural notes bigger. Make it bigger and bigger. Okay, so I think it is now readable. It is now readable. Let us move it a little bit here. Okay. Okay, so it's now readable. Now let us take it one by one and explain. So number one, we have at the top, framing plan, unit 1. Note, girders are straight and parallel. Okay, so they are all parallel. Okay, so they are on the general direction of the bridge. Okay, so structural steel notes. Number 1, all structural steel shall be AASTO. Okay, take note. What is AASTO again? It is a code. Okay, so AASTO M270. So that is the grade of the steel. AASTO. It did not use AISC because this steel is for highways and bridge application. That's why they have to follow AASTO. So AASTO is American Association of State Highways and Transportation Officials. Okay. So M270 grade 50 W and painted in accordance with System 4 of Article 442 thus be of standard specifications unless otherwise noted in the plans. Take note. The same is true in our country. Okay. We have specification up to the painting of the structure. Okay. Because painting, particularly painting of steel, which is a material that is very much susceptible to corrosion. So DPWH of our country is also having department orders about paints, and we have it on our blue book. We have it on our blue book, and we will tackle it once in a while. Okay? So therefore, this System 4 of Article 442B could be replaced by Department Order number of our DPWH. Okay? So you can replace and localize its application. Okay? Number 2, all dimension shows are horizontal or vertical unless otherwise noted. Okay? That is understandable, to be easily readable, to easily communicate to the construction engineers, project engineers. Number 3, all field connections to be 7-8 inches diameter, high strength bolts unless otherwise noted. So the design is to use 7-8 inches. Okay. Okay. That is the size of the bolt diameter. Okay. So when there are no specification found on the drawing, this is the default dimension of the bolt. So high strength bolt. Okay. So number 4, bearing stiffeners are to be placed normal to the web of the girder. Okay. So stiffener. Okay. Okay, stiffener meaning for better stability of the structure. Okay. So normal to the web of the girder. What do you mean by normal? We mean perpendicular. Normal means perpendicular in this context. So perpendicular to the web of the girder and shall be plumb in the final condition. What do we mean by plumb? Okay? In local dialect, plumb is pahulog. Okay? Okay? Plumb is pahulog. Local dialect. Okay? So meaning, it must be aligned perfectly in a vertical orientation. So number 5, permitted flange and web shaft splices shall not be located within 15 feet of maximum dead load deflection. Okay? Dead load deflection. Maximum dead load deflection. So we already know what we mean by deflection. We already know what we mean by dead load. And of course, maximum, no? Maximum dead load deflection. Okay? So it must not be located within 15 feet. Meaning, it could be placed exactly 15 feet or more. Okay? So flange, that is for flange and web shaft splices. Okay? Okay, flange. We cannot splice. We cannot splice. And we cannot make a flange connection within 15 feet. Okay? Okay? Parenthesis. Nor within 15 feet of intermediate bearings of continuous units. Okay? So, meaning to say, even intermediate bearings must not be within 15 feet. Right? So, next sentence. Keep 2 feet minimum between web and flange shaft splices. Keep 6 inches minimum between connector, plate, or transverse stiffener weld and web or flange shaft splices. Okay? So 6 inches minimum between connector plates. So if you are not using flange, but instead you are using connector plates, so keep it 6 inches minimum, okay, between themselves. Okay? Or even if you are using transverse stiffener, welded, and or web or flange splices, so that is the exact condition. So number 6, tension on the ASTO M164 bolt. This is under the standard of ASTO, size of the bolt. So the size of the bolt is metric because we have this name. This is the name of the bolt. Okay? Shall be calibrated using direct tension indicator washers in accordance with Article 440-8 of the standard specification. So take note, this is true, this is correct. Every engineering plan must have, okay, tension when we are using bolt, because the bolt, if too much tension, would be broken. Okay, so it would be broken. There's too much tension, tensile force. Okay, so there must be a department order in our country. So also, I am already familiar with this, but I cannot recall the specific department order. Okay, so this is for the use of other countries. This is actually in the United States. Okay, so in our country we are using department order. We have a specific department order number. series of year. Okay. Next, number 7, ends of girder shall be plumb in the final condition. Okay. This is just similar to this one. Okay. So, in shall be plumb in the final condition. Okay. Ends of girder. Okay. So, we have to make it sure that excuse me, we have to make sure that the girder is perfectly vertical. Okay. So number 8, bearing stiffener may require coping if final condition. Sorry. Bearing stiffener may require coping if wider than bottom flange. We need coping. What do you mean by coping? This is the first time I encounter this word coping. Not the English word coping. Of course, I am familiar with the English word coping, but I want to make sure if there is a technical meaning. There's a technical meaning of coping in this context. Okay? So, bearing stiffener may require coping if wider than bottom flange. Okay? So, let me or give me 1 minute to confirm what do you mean by coping. Coping. So bearing stiffener may require coping if wider than. So if it is wider than the bottom flange, it may be susceptible to rainwater, seepage of rainwater into the wall. So I think it has something to do with rainwater that might cause the water to stay and produce additional problems in the structure, in the construction material. Okay, so that is what we mean by coping in the building. So I am actually, so coping is preventing, okay, preventing okay. So coping is mainly exposed to extreme and mainly wet and dry. So it is better to do coping with materials that are resistant to sulfate action. So to prevent that sulfate action, so coping. So there are several definitions of coping technically with respect to structural. So I think this has something to do with water and the possibility of having the water producing more damage to the structure. Okay. So number 9, structural steel erection in a continuous unit shall be complete before false work or forms are placed on the unit. Okay. Erection. Okay. So we need to use heavy equipment, several, for example, crane, boom crane, to set up the erection of the steel components, okay, while the false work and forms are placed on the unit. Okay. So that is for temporary support, false work and form works. Okay, number 10, for temporary bend, see special provision. So there is another definition. Sorry. Excuse. So we have number 11. So fabricators shall detail diaphragm members and connections for steel dead load fit up. Okay. So that is an instruction to be followed by the fabricator. Okay. The fabricator of what? Fabricator of diaphragm. Okay. Usually, that is installer also of steel. So steel works. Okay. Okay. So, and if you can see, we have a box. Notice here for legends. So that is the legend. However, I would like to ask you a question. Do you have any question about those notes, okay, structural notes? Okay, so as you can see, the title of this drawing page is superstructure. As you can see here, superstructure, structural steel framing plan. So that is a framing plan. What about this one? So we can read that one again. So we have the legend for X. What do you mean? Field splice type. So X meaning you can use any, because X is a variable that could represent, for example, E. We already saw the value E. So E inside the box meaning field splice type. Right? So what do you mean by this one? This is the drawing for the bolt field splice. Bolted field splice at one of the two indicated location. It may be omitted at the contractor's discretion and replaced by full penetration welded shaft, flange splices, and web splice, or by a continuous web plate. See shaft splice details on the superstructure structural steel detail sheet. The contractor's choice shall be shown on the working drawings by review by the engineer. Okay, so that's all for this framing plan. So again, plan and elevation. Number 2, typical section. Number 3, framing plan. Let's go to number 4, girder elevation. Okay. So let's start it here. Girder elevation. Let's make it bigger, a lot bigger. So it is a lot bigger now. Okay. So this is what we call girder elevation. So this is the next content of the, so actually this is the fourth one. Okay. Girder elevation, fourth page. Okay. So AABB, then C notes 1 and 2, C notes 1 and 2 here. So we need to really see the notes because there are explanation involved. So S1, S2, S3, meaning is spacing, no? Spacing or okay, the distance between this bolt and this bolt. Okay, so okay. Okay, we have base 3, S4, here is 5, base 6, is 7, and base 8. So those are the distances. Okay. What can we have here? Center line 1 and 3/4 inches by 20 inches. That is that a center line? Okay. Let me check. Okay, so that is PL. I think this is plate. So plate. Okay. So plate line. Okay, so this line is a plate. And that plate actually is, so this is the description of the plate. The plate has the dimension length times width. No? So this is width times length. 1 and 3/4 by 20. So 1 and 1/4 by 16. So that is 8. So what about this? This is the web. So this is the flange. This is the flange plate. This is the web plate. So what is the web plate? So we have the dimension 38 inches by 62 inches. Okay. So this is okay. This is 316 inches. 316 inches by 62 inches. Okay. So that is for the web. Okay. Now take note of the location of the bolt. Here, located here, located here, here. So we have the, this is the top flange, this is the bottom flange. This is the web, so it is a W beam type of girder. What is this? 3/4 inch by 8.5 inch end bearing stiffener. Okay, so this is a end bearing stiffener of this beam. Connector plate plumb in the final condition. Typical. So plumb it in the final condition. Okay, so the same 1 and 1 port by 20. So 1 and 1 port by 20, this is 1 and 1 port by 16. So 1 and 1 port by 20, this is 1 and 3 port by 24. Okay, so it adds 4 inches here. This adds again 4 inches here. So from top and bottom flange. Okay, so top and bottom flange plate. Next, center line. This is the center line of the bridge, center line of the bridge. Center line of the bridge. Center line. So what else? What else can we find? So next, so that is our girder elevation. How does our girder looks like? Okay, so that is how girder looks like. Now the number 5, contents requirement of engineering plan for the bridge design. We have cross frame details. How do we connect the cross frames? Okay, this is how you connect the cross frames. So we have end diaphragms. We have intermediate diaphragms. So take a look, D1 and D5. So meaning to say, we can now understand what do we mean by D1 and D5. So that is the name of the diaphragm itself. That is the name. Okay, intermediate, therefore D2, D3, and D4. So there are 5 diaphragms actually. D1, D2, D3, D4, and D5. So 1 and 5, that is end diaphragm. So interior diaphragm, so we are calling it intermediate. So these are interior diaphragms. Okay. What else? We can further increase the so that's how we increase okay. So end diaphragms, those diaphragms that we talk about on the previous slide. So we have D1, D2, and D3. We talk about those things. So these are the details of that. The details of the diagram. The diagram looks like this. Okay. So we can increase its size even more. Okay. So, what is this? So this line are the center of the bolt connecting to the upper part of this. So there is an upper part here. Then this is the connecting bolt. So that is what 3/4 diameter by 4 inches studs. Right. So the diameter of these bolts or studs are 3/4 inches. So there are 4 inches length of each of them. So diameter and length, that is how we specify bolt, diameter and length. Okay. Span 1 foot, center to center. Okay. This is what we mean by this. So there are several studs or bolts and they are spaced 1 foot. So next, again, the center line of girder, center line of girder. So that is correct. So this is a C channel. Okay? This is a C channel C15 by 3.9. So what do you mean by C15 by 3.39? This is C channel. The depth of the channel is 15. Okay? So the depth is 15. 3.9 is the amount of weight pounds per foot. So how many pounds per foot is this C channel? So this is 33.9. Okay. What else? These dots are actually bolts. So HS bolt, typical HS bolt. What is the diameter? 7/8 inches diameter. Then we have a plate here. Okay, that is the gusset plate. This one. So this rectangle here, this is a very important gusset plate here. So this is gusset plate. Plate line shown MT 6 by 25. That is the typical dimension. So again, typically 6 by 25. So what about this one? This and that one. So 1/4. That is 1/4, 24 inches minimum. So what do you mean by that? So this is the welding description. It describes the welding here. So we will cover it when we get to the topic of what connections, welding connection, bolt connection, and so on. We will get to that, and we will explain it at the same time. Not today because there are several types of welding. Okay. Also with this one, so these are what welding symbols. So meaning there are weldings on this portion. Okay. There are weldings. Typical 1/4 by 4. What is the thickness of the gusset plate? 5/8 inches. 5/8 inches. That is the thickness. What else? 2 inches minimum clearance. 2 inches. 1 1/4 minimum. Okay, the location of the bolt. Okay, anything? Let's move to the next one. This is intermediate. Intermediate D2, D3 bend diaphragm. Okay, so this gusset plate is now on the bottom side. So it just reverses the previous drawing. Okay, here all of these black dots are bolts. Okay, so bolts. There are bolts here. Two spacing at 4 1/2. So therefore that is 9 inches. Let's go back to D2, D3, and D4. Top of the slab from the gusset plate. Typical UNO. I would like to find out if there are questions. So there are no questions. So let's just continue. So there's no additional information here. So gusset plate again here with the arrangement. The arrangement of bolt are as shown. That is the actual arrangement of the bolt. Those black dots. Okay. What about this one? There are 4 bolts here. 4 bolts here. So there are 6 bolts here. 6 bolts on the other side. So 1 bolt is 7-8 inches. HS bolt typical. Okay. So, connector plate or bearing stiffener. Okay. So we have the bearing stiffener. We have the typical angular bars. So this is angular bars. So pi by pi by 7/16. So what do we mean by pi by pi? 5 inches by 5 inches. That is what we mean by pi by pi. Remember, we are using English units. Okay. So the thickness is 7/16. Okay, the same is true here. Pi by pi by 7/16. These are the description for. These are actually the description for what? Steel products, there must be some level of precision. This is for surface. And actually this is not for surface. It is pointing on that is actually welding details. This is a welding detail. Okay. So next. Okay, on the bottom part, you have the following. Typical plans and web butt joint. So butt joint. This one. So this is what we call the web butt joint. So this is the flange butt joint. Okay, so flange and web butt joint. So grind smooth and flush on outer face of exterior beams and girders. Grind smooth. So we need that process. Okay? Typical gusset plate connection like this. So it is so detailed. Okay? Weld termination details. Stiffener and connector plate and so on. End of the web. So here. So connector and stiffener. This one is the connector stiffener. So this black portion, the welding. So these bold lines, they are welding, connecting two components. So this is the gusset plate end of weld. Okay. Okay. So these are the very important details. So on the last quarter of this page, shear connector details. Okay, take a look. We are going to design a shear connection. So please take a look. Okay, we have bearing stiffener detail, intermediate stiffener connector plate. So intermediate and bearing stiffener. So we have what? 3/4 inch. So 3/4 inch that amount. So typical. This is the connection can be connection. Could be a welding or the surface. Okay. Note, bearing stiffener may require coping if wider than bottom flange. Okay. Intermediate compression flange. Take note. Tension flange, compression flange. Take note of the technical term. Connector plate. Okay. So, and we already able to discuss each and every one. So, revision. So, anything with this one, that is revision. Cloud symbol, that is revision. Okay. So, who revised it? B. Peterson. When? May 19, 2015. Checked by Coletti. So we know that Dominic Coletti is a professional engineer, PE. Okay. Any other details? So these are very simple details. Okay, very simple details. So there's very simple details on here. We are okay. So let's go to the next. So next, so next one is bearing details. Let's make it a little bit bigger. So this is the, so how many? 1, 2, 3, 3, 4, 5, 6. So we are on bearing details. That is the 6th page. So, let us start with the most important parts. These are the most important parts. So let us start it here. Let us make it larger. Make it larger. Okay. So this part, table for loads and movements. So we have the table for loads and movements here. So bearing, location, vertical load, how much in kilopounds. So unfactored, take note, unfactored. So this one is factored. Okay. So if we say unfactored, we have yet to multiply the factor or the load factor. We have yet to multiply it. So when we say factored, we already multiply the load factors and sum it up, total it up. So sum it up. So add all of them, add all of the loads. So that is what we mean by factored here. Total movement in inches. We have bearing 1 and 3/16. Then at the bottom 1 and 1/8 inches. Okay, so it's always a good idea to present a tabulated information. Okay. So, where it is located, bend 1, bend 2, bend 4, bend 5. Those are the location of these bearings. Okay. So next important thing according to this author is we have here the contractor may substitute this bearing for the path bearings shown. So path bearings and these bearings are two of the most important type of the two of the most used type of bearing. For optional, this bearing see special provision. What else? What do we have? So then here, this box. What do you mean by that box? Okay, again, that is the same, the contractor. So it is just what? It is just this just expanded. So they just make it bit bigger so that we can read it. That's and let us do this last time, one by one. Let us do this. This is the last engineering content. That is what we call this. What we call bearing details. Okay. What additional details do we need? Okay. So let's start. Okay, let's start with that. So So this is our bearing detail. Okay, this is the bearing detail. Sole plate. So we already discussed sole plate on the bearings during our explanation of the different. We explained already the different parts of the superstructure, and when we discussed the bearing, we have the different types and the parts of the bearing itself. So sole plate, girder, center. What is the location of the bearing? Okay, this must be the piston type bearing. So piston, then cylinder. Okay, then cutaway plan. Okay, so for more clarity, again, we have section AA, we have section BB. Sole plate again, so we have the bolt. So this is masonry plate. Masonry plate. Okay, so cutaway plan, and cutaway plan. So there are several level of details. Okay. So next, we have the same cutaway plan, and we have elevation and plan. Details of the bearing. Bearing is located at the top of the pier cap or the pier itself or the column, and it is the lowest placed superstructure component. So that is the bearing. So increasing station is going here to the right side. So C asterisk note. Okay, we will look after that. C double asterisk note. So this is what? T and L. So T and L. So there is a dimension for T, thickness, L, length. What else? W or the width. Okay. Oh, this is the girder certain line. So asterisk, what do you mean? Dimensions L and T are to be determined by the manufacturer. So dimensions. Okay, percent slope. So it is given slope. Anchor bolts. So we have several anchor bolts. Masonry plate dimension. Masonry plate dimension. Okay. So this is the masonry plate. Okay, this is the masonry plate dimension. So we have here. So ABC. Okay. So plate M1 and M2. Where it is located, bent number 2, bent number 4. So here, bent number 1, number 2, number 4, number 5. So those are the bends. So there are 5 bends. Okay. So plate number is 1, is 2, is 3, is 4. So we already talked about this one. So I show you already where it is located. Okay. And then we have the slope and the width. Okay. So we have anchor bolts dimension 1.5 diameter with length 1 foot and 6 5/8 inches. So that is the anchor bolt dimension. Then here the masonry plate. This one is the masonry plate. Okay. Dimension. This one. Okay. So ABC dimension. So this is what we mean. Huh? Okay. ABC details. So next, let us go down. Okay, so we have here section AA and BB. So that is on the upper part of the drawing here, this drawing. So that is also part bearing detail. This is the masonry plate details. So some of the masonry plate detail, the location of the hole for the bolt. Okay. This is very easy to understand because here, this is the elevation view. This is the plan view. So these are the dimension. So from this point to this point, that is how much B. From this point to this point, from this plate dimension to this A. So and we have C here, the dimension C. So ABC dimension. So we have the dimension on the table. We have tabulated value. So that's why we have those things. And we can find out what do we mean by M1, M2. This is here, M1, M2, and M3. Okay. So 5 is the requirement, though 10 required. Okay. So M1 and M2. So how many do we need? So total of 10, 5 M1 and 5 M2. So how many? 10 total. So what do you mean by M1, M2 here? That is one is different dimension from the other, and we already showed the table. How could we be able to distinguish? See here, M1, M2, masonry plate. These are the dimension ABC. Okay. Look, M1 and M2, there are differences between the dimension ABC. Here, A is 2 feet 1/2 inch. This one M2 is 2 feet 2 and 1/2 inches. Okay, and so on for B and C. They are also different. Okay, table for loads and movements. Then we have a complete list here. Okay. So in this case, DC, DW, LL, and IM. Temperature at time of setting, bent 1, bent 5. So setting of these steel elements. So we need the correct temperature, because matter expands or steel expands when heat is applied. So this is steel. So how much Fahrenheit? 90 Fahrenheit, 60 Fahrenheit, 45 Fahrenheit. So these are the values for bent 1 and bent 5. So the same. Not the same here. 1/8, this is 1/16. So the same. This is not the same. Okay. So what is the asterisk? Asterisk is the correction for end rotation due to wave tube slab and composite dead load. Okay. So it's very clear. Every information is now clearer. Okay, let's take a look on the last portion of the last slide. Guide key detail. Guide key. This is what we meant by guide key. So there is a piston and steel top plate. So in order for the steel piston not to be derailed, so there is a key so that the piston will always move on that specific orientation because of this key. Okay. So TFE facing, so meaning this is the plastic or polymer component. Stainless steel facing, so stainless steel is there. This is the TFE. TFE is polymer. Okay. Okay, so everything is already explained, including this one. So this is the sliding surface. That is the sliding surface, actually the piston. Sliding surface there. That is the piston. That is the sole. Okay, so sole, plate line, okay, masonry and bury in this center line. Okay, so that's all about everything in our what this is about bridge plan. Okay, that's all about it. So bridge plan, engineering plan set. Okay, the complete set is the listed contents of the pages here. That is the complete set, and how it is organized. How it is organized, we mean how it is sequenced. So the organization is this one. This is the first page. Second page, that is the meaning of organization. It is organized in this specific manner. Okay. Okay. So anyway, we are through. I would like to take a look on your questions if there are. So I will stay here for 15 seconds, then we will provide the next live stream topic. Again, this is Dr. AP, Preaching Engineering for Nation Building.